Hello students, today we'll be solving the second problem of the problem sheet number 4. Here the problem says that mass m1 and m2 are attached with a spring of stiffness k, for which the numerical values are given as m1 as 10 kg, m2 as 15 kg and stiffness k as 320 Newton per meter. Problem is a problem of semi-definite system because the figure clearly shows that this is a problem of semi-definite system where equation of motions for the first mass can be written like this and equation of motion for the second mass can be written like this. Remember always these two displacements x1 and x2, whenever you are writing for mass m1, it will be always x1 minus x2, and whenever you are writing equation of motion for the mass m2, these displacements will be x2 minus x1. So this is the only difference between these two equation of motions for these two masses m1 and m2. Now let us assume the solution for this particular problem to be simple harmonic motion, where we are expressing x1 and x2 as a1 sin omega t and a2 sin omega t, which are the two common forms of solution of simple harmonic motion. In the next step, we are finding out the acceleration for the displacement x1 and x2, which are given like this. Acceleration for x1 is minus omega square a1 sin omega t, and acceleration for x2 to be minus omega square a2 sin omega t. Now putting this sets of equation 3 and 2 in the equation set 1, we can find out that the two equations will take some form like this. Now there arises a question that where this sin omega t has gone. Now the answer is, in case of this type of problems, whenever we put the acceleration and displacement in the initial parent equation of motion, we consider the maximum value of sin omega t to be there, and which is 1, and hence we directly write minus omega square a1 and minus omega square a2 in place of the accelerations in the equations of motion. Then we will be getting the amplitude ratios from the first equation as this: a1 by a2 is equal to k by k minus m1 omega square, and from the second equation of equation number 1, a1 by a2 can be calculated as k minus m2 omega square divided by k. As we saw in the last problem of this problem sheet number 4, both these two amplitude ratios will give you the same numerical answers at the end. Now the frequency equation, this can be calculated, this can be obtained from these two equations only. Since left hand side of both these two equations are equal to each other, hence these two right hand side part will be equal to each other, and by simplifying this we can get some equation like this, which clearly shows that one value of omega will be equal to 0. Hence this entire system of this equation is a semi-definite system. So further simplifying the equation, we get ultimately omega square to be equal to k into m1 plus m2 divided by m1 into m2. So now using the last two equations, we can find out that the natural frequency omega 1 is equal to 0 and omega 2 is square root of k into m1 plus m2 divided by m1 into m2. Now putting the values of k, m1 and m2, we can calculate the value of omega 2 to be equal to 7.30 radian per second. Now using these two values of natural frequencies omega 1 and omega 2, we can calculate the amplitude ratios like this. Using omega 1, the first amplitude ratio a1 divided by a2 is equal to 1, and using the second value of natural frequency omega 2, which is 7.30 radian per second, we can calculate the amplitude ratio to be something like this, and finally we get the value to be 1.49. Now this is a very important point where we can show that when there is a semi-definite system, the first natural frequency is always equal to 0, and hence the amplitude ratio is equal to 1. And the second natural frequency bears a value which is different from 0, and because of this value, the second amplitude ratio is always different than 1. Thank you.